Hello everyone, I'm Jackie. I want to apologize in advance. I'm extremely jet lagged and basically unconscious right now. So if I'm speaking a little too slowly, kind of like go like this or something, and I can try to speed up. And if I'm speaking too quickly, reverse. I'll try to pay attention. So I'm jet lagged because I flew in from San Francisco on Thursday, and I live in San Francisco. I work at a small stealth mode robotics startup in the city doing really fun stuff. If you're curious about it, you can ask more about it offline. That is not what I expected that interface to do. Okay, okay, great. I'm going to stand here. So I wanted to give a general application-oriented presentation, and these kinds of presentations are sometimes, I think, received in a mixed way at C++ conferences because people want to come here and often want to talk about really cool, more theoretical, language-level abstractions. And I totally agree. Those are really cool. And also, they don't make any money and don't do anything in real life, unfortunately, unless you apply them to real-world problems. So my goal for this talk is to discuss some real-world problems and try to extract some abstractions I think are interesting to get everyone else in this room really excited about robotics. So we're going to talk about some tools and techniques that people use. You'll kind of learn about the state of not the state of the art, or really just the state of what people use in the field, and a little bit about what I think we could do better or what we could do in the future. So you might be in this room because you've heard that robotics is really exploding right now. It's this very trendy thing. It's a buzzword, automation. People are buying all these robotics startups like Google, and there are these self-driving car companies coming up. It feels like science fiction reality we all dreamed about is actually happening. And maybe you'd like to pivot into this field, or maybe you are already in it and you're curious to see what another C++ program in this domain has to say about it. So I'm here because I'm a total nerd, and I just fangirl out and take selfies when I encounter these things in real life. And they're increasingly appearing in this kind of tech bubble area that I live in. The middle picture is from the Palo Alto shopping center, where there's a security robot that wanders around, and I'm not sure it actually secures anything. But in fact, many of the things I'm talking about today, the software we're talking about will probably be running on that robot. And I think that if you're interested in a really hard domain and you're using a really powerful tool, you'll never be bored. You'll always have some interesting problem to give you headaches and also make you feel really awesome and smart if you end up solving those problems. So if we're going to talk about this field, and in many talks that I give, I try to come up with a satisfactory answer to this question, we actually have to define the problem. And there's a very amorphous the word robot has a very amorphous definition. It doesn't need to have physical embodiment. I mean, like websites have that robots.txt thing that just refers to bots on the internet that crawl websites or whatever. But I like to make this interesting, I like to require that a robot refers to something that exists in the physical world. It has hardware. It's autonomous, or it might receive limited commands from a human in the loop. It makes decisions in real time, whatever that means, in a short amount of time based on sensor streams that come in, and those inform its next decision in the environment. And to make things really interesting, it probably has some state machine behaviors. It's not just it's not just translating the sensor stream directly to an output. It might be storing that state and then making long-term decisions about the state that's accumulated over time. So basically, a lot of what I just described, if you think about abstracting the problem to what are the kind of computer science programming fundamentals that you need, the overall system design might look a lot like a video game or really any large-scale, real-time, soft real-time, hard, whatever, system that you might implement. So think about, you have, for video game example, you have user input from a keyboard, and you have to transform that into something that steps your overall state machine, shows output to the screen. But I think the really fundamental difference, and one thing I'll focus on today and the problems we address, is the problem of perception and localization. These are problems of approximating the state that you are interacting with that exists in reality that you have no actual ground truth for. So in a video game, for example, you know your location and you can transform perfectly to every other thing in the simulated world. You know for a fact, based on some metadata, type tag, whatever, if the other entities in the scene are enemies or allies, if they're power-ups, you know exactly what that behavior is. And in robotics, everything you interact with, that is going to be an approximation. You can approximate it very well, but it will still be an approximation. So here's an example of that. Localization is a subfield of robotics that is basically navigating where you are, figuring out where you are when you're essentially blind. You have to infer your location from an offline map or representation of the world and your sensor data. So what I usually say is someone kidnaps you and drops you in the woods, and you only have a map and a compass, and you have to find your way home. And that is what it is like to be a robot. When someone flips your power switch on, you might load some data from your hard disk that says, I have a general idea of what the world looks like that I've mapped out, but also I have this collection of points or pixels from a camera or whatever. And I have to figure out where I am. So this is a really fundamental problem, and some people like to throw a lot of statistics at it to make that work. I'm not going to go over this algorithm today, but if you want to look it up, I'll basically, this is motivated by particle filter localization, which is you keep multiple theories about where you are, and you use statistics to infer what the best theory is. So there's going to be some math in this presentation, and I know that a lot of programmers are people who didn't really like math in college, but liked this other thing that had a lot of logic and cool stuff, which is programming. But I swear it's not going to be a lot. Here's a fundamental statistics fact. If you're calculating the probability of an event, and that event is that multiple other events occur, and those events are conditionally independent, meaning that they don't have any correlation, or they can happen independently of each other. You calculate the overall probability by multiplying the probabilities of the individual events together. And the intuition here, which I think is interesting, is probabilities are between 0 and 1, so this number gets smaller and smaller as you add more events, which makes sense intuitively, right? Because if you're calculating the probability that lots of things happen, it's less likely they all happen at the same time than just one thing happening. So this is interesting, and I swear we're getting to real code soon, like really soon. This is interesting because a fundamental sensor that we use outdoors especially is a laser scanner. A laser scanner is the thing that emits beams and bounces those beams, laser beams, off of things in real life, and it times how long it takes for the laser beam to return to the sensor, and then it figures out a distance to a thing from that. And it has about nearly 1 million, let's say 900,000 points or scans, individual points it sends out in one scan. And in order to calculate the probability that you received a particular scan when you're in a particular state. You have to multiply together the probability of receiving every individual point in your particular state. So you have to multiply together a lot of tiny numbers. So, like, why do we care about that? Well, you're probably going to underflow. And even if you downsample points, if you're multiplying together a lot of numbers between 0 and 1, let's say it's like 0.1 to the 900,000, because it's 0.1 times 0.1 times 0.1 times 0.1, et cetera. You get a really, really small number. Even if if you're using doubles or long doubles, it's very small, and you will get arithmetic underflow, and you may see nans, you may see negative infs. Your compiler is going to treat that in funny ways. So what do we do about that? There's some libraries that people came up with that are very Boost-like, or maybe in the Boost library incubator, that are kind of cool. So, for example, Robert Ramey, who's really prominent in the Boost community, he gave a presentation at CPPCon about this thing that he calls the Safe Numerics library. I took a look at it, and it employs some interesting techniques where when you assign an arithmetic type to basically when you calculate the result of any operation and you assign that arithmetic type, it checks for overflow or underflow, or it checks if you're exceeding the boundaries of that type, and wait for it. If you violate that boundary, it throws an exception. So I really wanted to benchmark this because it seems like you would want a library that handles overflow and underflow really well, but if you're calculating if you're calculating the conditional probability of 900,000 points, you're doing 900,000 floating point operations, and you have a timing constraint on that, and you already have other things in your critical path and in that processing step of that sensor data that are expensive. So you're going to be looking stuff up in a huge map that represents your whole world. You probably don't want to be trying and catching an exception every time you multiply something together. So, okay. So I really wanted to benchmark this for you guys today. And I was really planning on doing that. And then I ran into a really interesting problem, which is that the way that the library is written, it just doesn't work on floats. And that's because the way he's implemented it is that the minimum and maximum values for every safe numeric type are non-type template parameters. So it just doesn't compile. So it's not mentioned in the documentation anywhere. It's kind of unfortunate. And I think this is an interesting case, and because in robotics, I really want to be using the best tools and the best cutting edge libraries and things that are syntactically really clean. Because when you have to write out code that has a lot of complicated math, you want it to essentially look like you took it out of a textbook, and you can look at your code and then look at the textbook and say, that's the same thing. So where are my bugs? I don't know where my bugs came from. And then you can isolate, if you do have a bug, that it must be something in your implementation, it must be a timing problem. If you miss a deadline in this kind of real-time programming that we're doing, your program is incorrect. And that is often the cause of subtle bugs if someone doesn't benchmark, which a lot of roboticists don't necessarily do. Oh my God. So I wanted to use this. I also wanted to reference this other competing safe numerics library, which does not use exceptions. It uses expected, which is kind of a lower cost error handling mechanism, which I found interesting. But it also has no support for floating points floating point numbers, floats or doubles. So localization is a cool problem. Also for reference, the way a lot of people implement this is they essentially don't check for overflow or underflow. They transform the problem into log space, which means you're not multiplying together tiny numbers, you're adding like normal sized numbers. But you still have the danger of overflow or underflow. Like if this localization algorithm is running on a self-driving car, then you would need those checks for safety. Because, yeah. So localization is really an interesting problem. But the other really interesting problem unique to robotics, I think, is perception. And perception is the problem of identifying and categorizing and localizing, or finding the position of objects in the environment. Objects besides yourself, because you localized, whatever. And there's a lot of, okay, yeah. So the way people used to do this is some like history. Many years ago, Marvin Minsky developed this thing called the perceptron and was like, this is super cool. This is like how brains work, neurons and stuff, and we can use these to categorize images and computer vision. That's like making robots see things. That's really solvable and easy. The problem is that we didn't have computers that were good enough to train neural networks at the time. So people came up with these geometric approaches to computer vision. And when I say geometric approaches, I mean this technique of using specific knowledge about an object and some geometric trick to figure out, and probably some really slow like scanning algorithm to figure out where something was in a picture and identify it as like, this thing has 4 sides, it's square, and I know that tables sometimes are square or rectangular, and they have 4 legs that are like long things poking out. So I've just built my table identifier from, some geometrical specifications. I bring this up because this is something offered by one of the coolest, for a while, libraries to solve this particular problem, which is called OpenCV. It's about 16 years old, which is like, to me, that's a long time, many years old. It is a really big project, and it has basically everything you could ever want to when you're manipulating 2D images, doing geometric transforms on them, whatever. And I wanted to show you guys a code example. Can you guys see that actually in the back? It's pretty big. But, okay. Yeah, I wanted to show over in a code example because OpenCV, it was originally developed as a C library, and they were like, we're going to have this really efficient, contiguous representation of a matrix that you can stride through, and you can change the representation of the channels, whatever. And okay, so people want to use C++, so we'll make a C++ interface that uses standard vector and some other cool stuff. But the library in general often looks a lot like C. There's a lot of positional arguments, and I mean like a lot of positional arguments. So basically anytime you see an all caps tag, that's usually specifying some like setting or mode, and there's like 10 per algorithm, and they just appear in arbitrary places. There's also Python bindings for this library, and they use, like optional argument named parameter everywhere, right? And people, that's not very idiomatic in C++, although I saw it a lot today, so maybe we should all go for that. Okay, so this is trying to find the contours in an image. And it's like super cool what this thing can do. It can just take this cartoon fish image and find all of the edges in it. And it's actually, it works quite well. I showed this cartoon example. It works pretty well on real picture, like photographs. And you can imagine saying, I'm going to build my perception engine based on finding all the edges and then taking contours and taking their area and then saying based on the shape of a thing what kind of thing it is. But that approach starts not to scale very well. Before I move on to something I just foreshadowed, I'll talk also briefly about PCL, which is like, it calls itself kind of OpenCV for point clouds, which are 3D representations of the world, something you'd get from a laser scanner, which we already saw, or maybe like Xbox Kinect 3D camera. It's pretty cool. It does not have Python bindings, the C++ only. It makes pretty heavy use of CUDA for performance reasons. And it can do things like it can do color segmentation. That may be kind of hard to see, sorry. And here's another code example of kind of like the state, the idiomatic state of what these libraries are like. So we've got a bunch of shared pointers. This like pointer type def is a shared pointer because this was designed before C++11 and we didn't have auto, so anything you could do to make type names smaller is like big win. Yeah. There's this thing that's like you type erase a tree and then you call it a search, and then you pass that as a search method to your region growing RGB object. But region growing RGB is actually an algorithm, which is a stateful algorithm. It takes parameters and stuff. But then the output of this is like, oh my god, it found out where the chair legs are, and it also figured out that there's like this chair legs, and then this other part of it that's a place where you can actually sit. And these markers are like toys on the ground. It's a bit hard to see. I didn't have the reference image where it was taken from. So see, these toolkits are very powerful and also often like super painful to use. Like these are the like simple hello world examples. They wrap a lot of like research code that people have open sourced, and they're kind of in vogue because you can get off the ground really quickly to prototype, and you kind of have to like tune parameters for a really long time. But as I said before, these geometric methods, people developed them for a while and then realized that maybe for identifying objects which have a certain semantic meaning to humans, it's just not scalable. And that's especially for things that don't have these like hard edges that are easily described by math, like faces or animals or cheeseburgers or whatever, like blobby things that might be really important to categorize because you don't want to run over a human when you are a robot that doesn't know any better. So that's why people are really into deep learning right now, like really into it. There was this other conference last week called SLC, where I think the CEO of NVIDIA gave a keynote or a talk or something that was like, deep learning is the thing. You guys should all buy NVIDIA hardware. And I don't disagree. NVIDIA is really awesome. So deep learning, it sounds like it's going to change the world, but what is it really? Well, I already alluded to neural networks, which are basically, they're just graphs. They are collections of nodes that are connected by edges. Usually, I think maybe it's not just a DAG, it's a directed acyclic graph that people basically segment into layers. And those layers are important because your input layer represents a class of object that you take as your input, and your output layer is some conclusion that you've reached based on your input and this learned function. And the function is represented by the connections between the nodes. Basically, you take the value in your node and you apply some function over that value based on, and you have some parameter that's a weight, and the weight is associated with an edge. And you learn those weights usually through some statistical error minimization process, and the trendy thing is called gradient descent. Okay, whatever, you don't really need to understand that unless you are directly implementing those algorithms, And people have developed a lot of really good frameworks around this kind of thing. Deep learning specifically just refers to a neural network with many layers in the middle of that network. So this is an illustration of the VGG network, which is a pretty famous deep network. It turns out that there's this like black art of designing layers and functions that connect the layers to reach a really useful conclusion. So this specifically illustrates, you take this picture and you reduce the dimensionality down to one vector. And that vector actually represents different categories. So what you do, sorry, I forgot to mention this in the last slide. What you do is you take a labeled data set, you do the statistical analysis on it, and that is how you learn the edges, the weights and the edges. And then when you run it through a kind of a test set, or when you're running it in production, you want the propagation through this network to be like super fast. And okay, that's interesting. We've got this is the Google net. So I believe the paper a while ago that they trained it to detect cat faces because cats are the basis of memes in academia. I don't know. This is I think 30 layers, and the colors correspond to operations in the layers. So this is a convolutional neural network. Convolution is basically when you take two signals. They could be images, or they could be some artifact of other functions on an image, and you smooth them together. When you first look at it, it kind of looks like it's like O of n squared, but people have these fast approximation methods that get you down to n log n, basically, yeah. And you have some other like more expensive operations scattered through here to reduce the dimensionality. And the way they built this is through like a lot of mini nets. So why is that interesting? Well, we're getting closer to finding the dimensionality of the problem so that we know what tools to throw at it, right? So when you are driving a car, or when you are driving in real life, you probably want to be detecting images really quickly. So a canonical frame rate that people go for is 10 hertz. And that depends on how fast you're going, and also the like safety criticality of your situation. If you're in a really safety critical environment, you also probably want to have a high false positive rate, meaning that you're more likely to falsely detect that something is a person and avoid it. But you really don't want to have a high false negative rate, which means that you just didn't categorize anything and you just are about to go into the area where the person actually is in real life. And that also informs how we evaluate these networks. A lot of people, just based on the limitations of the state of the art today, we have these really high resolution cameras that will give us like, you know, at least 1,000 pixels with, but a lot of people usually downsample those to be like between 200 and 500 pixels. And we have these really deep networks because the innovation a few years ago when basically Andrew Ng made this discovery that deep networks are like quite good with pictures, and there's this magical stuff that happens when you convolve this function around, and that makes this quite fast. And this is, I was going to show this YouTube link, but that, if you are watching it online and you click on it, you can watch a really cool demo of a car driving on the highway detecting cars like really quickly in bounding boxes that are like move and shrink because it's detecting the position and the size of cars on the highway. So how do people do this? Well, what's really important basically is GPUs, and that's why NVIDIA is getting in this game of deep learning and robotics, and also why they have been making some like incredible innovations lately. Do we have any water? No. Okay, that's fine. Sorry if I start coughing. So I would probably recommend everyone, if you have like one takeaway from this talk, it's you should learn something about CUDA and GPUs. First of all, because it's really cool. But second of all, because the kinds of problems that we're facing, thank you, really appreciate it.
Thanks, Odin.
The kinds of problems that we're facing in robotics are highly parallelizable. If you have to do a lot of operations on a very like large input set, that tends to translate very well to GPU programming. And one thing that I find really cool, like fun fact, for example, is I seem like a really big NVIDIA fangirl, but the the TX1, which is this like super weird hardware that they made that is a 64-bit ARM processor. It runs an operating system that it's basically the strength of like a cell phone with this insane or like for that kind of device, like really impressive GPU core array on it. And they've added 16-bit floating point precision instructions to it. And that's important because in robotics, we don't always really need more than 16 bits of floating point precision. The kind of precision in your calculations, if you're estimating how far away something is, for example, you probably only need to be like within millimeters accuracy. So that gives you maybe an intuition for why less precision might give you a speed up, because then you can do really creative optimizations with how you stuff instructions and all that fun stuff. And I'm not going to try to explain CUDA programming here. I'm like way far from an expert. So I would recommend seeing a talk by Justin Labar, who's an LLVM developer who works on integrating CUDA with Clang. It's also a really exciting fun fact that our C++ compilers might soon have native support for CUDA, which is it's a C++ extension that's not standardized by ISO or whatever. So, and it's closed source, which is like a total bummer, but also associated with really great hardware. So it looks like we have no choice but vendor lock-in for a while on this one. So basically any deep learning framework that you're going to take seriously today has some CUDA backend. And I think that these are the trendy names that a lot of deep learning researchers use. So Caffe is one that's particularly popular in the research world. It's quite fast. Every layer has a, like pretty well encapsulated like CUDA functions associated with it, and then a C++ interface over it, and then there's this high-level Python interface, or you can use a C++ interface. But it's the Python interface is quite nice because you can kind of in a REPL interact with a machine learning model and then train it, and then you can serialize it, and then you can save that serialized representation, then you can come back and retrain it on a different data set, or you can take a network that somebody in a lab trained like 10 years ago, and then you can take that and tune it on your own pictures, which is super cool. The way you specify the schema of a network, kind of like those diagrams I was showing before, is this protobuf-based thing that it's very clean and has curly braces, whatever. But also, like, whenever you download it, you have to build it from source, and you have to go through this makefile where you specify, like, this is the lower level basic linear algebra subroutines library that I'm going to use, and you could get like a huge performance speed up if you got to enable a particular library. So that's fun. It's kind of I think of Caffe as like a little bit more hardcore versus like TensorFlow, which is like super well supported by Google. And so like Justin, who I just mentioned, gave that talk, actually works for Google, and probably they're very invested in GPU technologies. So TensorFlow is great, and also for serious stuff can be like really bad. And they have some problems with like not properly inlining certain calls that lead to like huge matrix cop use, and their representation of the computational graph is all in Python and not really well optimized. And apparently that's at least the part that they've open sourced, that's a huge bottleneck for people. And these are some other names you might hear. Lua, oh my god. Okay, so then there's this alternative, and it's called dlib. And it's an old project, and surprisingly, when I talk to robotics people, a lot of them have never heard of it. And I've also never used it for a serious project. It's like kind of amazing because you can specify networks not in some schema file that you deserialize and then load in or whatever, but as template aliases. Like, this is cool. Like, this could be really great. And then you get like 10 angle brackets at the end. And this is probably why it's not very popular with robotics people, honestly. Researchers are not interested in template metaprogramming. I have no idea why. Template metaprogramming is awesome. But dlib, it's pretty cool, and this example is from a program he wrote to detect dog faces and put glasses on it, and mustaches. But this is from a blog post that the creator wrote where he shows that the network that he made for this and faster RCNN, which is considered state-of-the-art in Caffe, actually has comparable performance. So I think that, I don't know, I've personally learned from putting together this presentation that we should take dlib very seriously. Okay, so does anyone have questions about perception before we move on? Okay, great. So once you actually perceive things, you may want to move that data across a boundary, across a process boundary or across a network boundary. And this is interesting because if you're building a really specialized system, it's probably more efficient to just stuff everything into one process if you can. Like your whole robot, it would be great if it could just be one state machine and it steps through that, and maybe there's some like hardware multi-threading for efficiency, but there's like mostly one thread or one context. But unfortunately, it's just a fact that communicating to different machines is just like how life is in robotics, because you have to connect sensors to a computer, and those sensors probably have their own MCU. You have to connect your computer, which calculated commands, to motors, and those have motor controllers, which also have their own MCU. And you might be receiving commands from someone who's like stationed in an office somewhere who's figuring out where you need to go next, and then that has to be sent over the cloud. And okay, also, and this is a bit more interesting, well, this is kind of a critical section as well, is fun fact based on the current state of the art, people still struggle getting real-time performance for accurate detection using deep convolutional neural networks, even on like the NVIDIA TX1, which is considered state-of-the-art hardware. So you might have an entire computer that is dedicated to perception, because you've basically like pegged your you've pegged your GPU doing detection, and you might not have a lot. You might also be doing like compression or something. You might not have a lot of spare cycles to spend on also marshalling data or like doing localization, what we just described, and hitting your real-time deadlines. Okay, so that hopefully motivates why communication is important. And also, another thing that a lot of domain experts in robotics don't want to deal with. Like, they don't want to think about Byzantine generals and why sometimes messages don't come in when you expect it to, like why this TCP connection is blocking so much. Like, they're just not interested. They just want to do the math thing or the neural network thing. So there's a bunch of solutions people have come up with to abstract away this communication layer, whether it's between processes or between computers on a network. And that, you know, people have like funny language to describe these libraries that marshal information in this way. It might be a runtime or a middleware, or like, you know, words that people don't really use in real life often. So, okay, so what are some things that are in current use or candidates for this job? Well, the project that I used to work on that a lot of people use is called ROS, and it is a middleware framework with a lot of really great tooling that is great for prototyping. So it is also full of old school idioms that really can make people feel bad about themselves. So it's pre-11, and so you can only serialize custom data types that you specify that you run through a code generator across the network. And also, if you have distributed parameters that you change at runtime, you also have to specify those to a code generator, and that kind of complicates your build step. And you, one thing that really kills me is you can't just natively pass a lambda to the callbacks. You know, you have to pass a function, and if it's a stateful function, then you have to use boostbind to bind your callback to a class. And these are like little details. However, it is committed to a really great framework for rapid prototyping, visualization, and has these like open source bridges to existing drivers that are really popular, and kind of lock into a lot of like popular libraries and translation layers for their data types, like PCL and OpenCV, for example. It's like very tightly coupled. But that design also comes from an era where, or it comes from a community where generic programming wasn't really a thing. So it's like, oh yeah, we need a lot of boilerplate for translating between these different data types. Okay, so the people who made ROS decided, well, we've got this big framework that people use in robotics, and we need to update it. You know, programming has come really a long way since the year 2008. We're going to use modern C++. It's going to be awesome. We're going to use a middleware that is all standardized and stuff and grown up so that people feel like the shortcomings of ROS are addressed by this. Unfortunately, it's not finished yet. And it's, I think, going to be a while until it's really ready for production. One of the interesting things about ROS is that this code generation step for sending messages across the network is really important because of cross-language communication. So another fun fact that we've seen, or maybe a recurring theme, is that Python bindings are really popular, especially for these neural network frameworks where like it's absolutely prohibitive to implement the kind of performance we need in Python for neural networks. domain experts really prefer Python for a lot of reasons. Okay, but there's this middleware framework which is really cool, which unfortunately does not have Python support, but could do a lot of the things that ROS does. It's called C++ Actor Framework. You may have heard of it, maybe not. It is really excellent performance, and it offers this implementation of the actor idiom. It would accomplish a lot of the same like publish, subscribe stuff that people like in ROS, basically like how do you get your callback to happen when the thing arrives. A lot of people working on robots have difficulty recognizing where to use existing frameworks like this that may be like really performant and maybe were designed for a different domain but could be plugged in because they don't necessarily have the right tooling or haven't heard of it or whatever. But I see a lot of potential in CAF, as the creators call it, because they are really interested in low cost and usability. They're also really interested in embedded domain, although I don't know if the implementation is all there yet. I think my monitor's falling asleep. Because they basically have experimental support for Riot OS, which is a real-time operating system, which is open source. So that's one interesting lead. So, okay, so let's say you've looked into these libraries and you've like done the ... step of that first slide, and you're now doing the other like 80% of the work, which is testing. So testing is really important, and that's because you have like huge combinatorial explosion of your input space is happening. You have really big inputs like a laser scan and pictures, and you reduce those to, or you have these individual components that reduce them to small things, like so the output of your localization is a pose, that's like 6 dimensions, and the output of your neural network operations on pictures, that's like, a thing and a point and a bounding box. But those are over continuous domains. Like anything, like it kind of feels like anything could happen. Like you should prepare while testing a robotic system that literally anything could happen. And it might be like maybe you decided to write all your software for Linux, and you have non-deterministic thread scheduling effects happening, and that's why you missed some deadlines that caused a subtle bug. Well, maybe you should have made different decisions about your software architecture or made your system more robust to those kinds of effects. But they can affect your tests too, and you should be conscious of that when you write them. I think, so the input space is really big and like confusing. And so it's one approach to that is writing your tests so that you like address every case, like you have regression tests for every bug that you ever encountered when you were driving the robot around in real life. That does not scale. And I think a better approach is if you write these like self-contained modules, you can unit test them really well, and you can apply sanitizers or static, compile time static analysis or static sanitizers, which are dynamic analysis on individual components. But what's important, and what a lot of people have trouble with this discipline, is when you have a software project that has all of these dependencies, like I just described, a bunch of libraries that you're going to link to, it's kind of hard / impossible to use the sanitizers unless you recompile the entire binary that you want to analyze. So keep that in mind. So yeah, there's going to be a lot of stages in your pipeline of testing. You might be one of the lucky / I don't know, maybe lucky people who have access to simulation. And testing in simulation is like, sounds like a really cool idea. So let's say you have a physics simulator that mimics reality perfectly. Like you have photorealistic images, so you can run that through your neural network or something. First of all, creating that piece of software is really hard. It's like making a video game, but worse. It also might lead you down the wrong path. Like, things that work in simulation will not necessarily work in real life. Again, you have to prepare for everything. Live testing is very important, and I think for me as a software engineer, and when you're working on a robotic system, it's really tempting to actually just sit at your computer and like write as much code as possible, or write as much code and as many tests. Sorry, as little code as possible and as many tests as possible. But and then like hesitate to actually go out and take it out into reality. But that's like the point of what you're doing. So when you're live testing, it helps to have really good live introspection tools as well for debugging. So that could mean you basically publish, and that's why, again, communication is important, publish a lot of metadata about what the robot is doing as it's running, and then visualize that in some like nice OpenGL rendered thing, because everything you're doing is in 3D probably, and 2D is not very informative. So like, you guys all know this, of course, but in this domain, testing can be very different from what you're used to. And running it in a kind of continuous integration way where you catch bugs, when you weren't even thinking about it, that can be hard. And isolating those bugs can be hard. And like, nobody's written a book that's like how to do robotics testing yet. Did that transition? Okay. So, how much time do I have?
5 minutes.
Okay, I'll talk really fast. That's fine. We're nearly at the end. I go to these conferences because I'm like really excited about the future of C++. And the robotics tools are not necessarily there yet, because it takes a lot of work to get these systems working in real life. Like, they're very complex. Sometimes I beat myself up about it, but like, making a robot's really hard. And there's some cool things coming up in standardization that help us. But the message that I want to send is this does not solve like our problems. People still need to do the work to make it happen. So there's some like cool stuff you might not have known about in C++ 17. One thing I'm really excited about is parallelism, which is this kind of syntactic specification for parallel standard algorithms like for loops, etc. There's also another like maybe lesser known thing is this thing called polymorphic allocator, which is a kind of a runtime alternative to the like compile time allocator interface for standard library containers. And I also think like syntactic improvements help everyone's productivity. Then there's stuff on the roadmap for later. Probably after the robots have all killed us, I don't know. So modules are great for everyone, of course, and I like really feel this one because the dependency chain in the work we're doing is enormous, and it also used to be part of, and still is part of my job to help manage that and run the build system, and the robotics people came up with their own build system and package abstraction layer to manage all this stuff, and modules help us a lot. Still, for cross-platform projects, we need some way of managing that, but like people are always complaining about C++ package management and linking, and understandably. And this is also like way out there and something that I talk about all the time. But I'm like really excited about reflection, and it's because when I kind of before I learned about things like reflection and also like a lot of metaprogramming tricks, it was like I didn't have the right language to describe what I wanted to do, which was to manipulate types and to write generic functions without knowing what that type was, right? And that's such a beautiful moment when you discover you can do that. And the idea that one day we'll have a standardized way to reach into the fields of types and do stuff with those when maybe you have some unified like concepts interface over something that helps you out. That's very exciting. And I think I was reading a blog post just the other day about how some people were like, well, we don't like using C++ compared to like Java because there's no reflection interface. And there's just such better tooling that has evolved around languages that have good reflection, because you can debug them better, you can do live debugging better, You can write generic debugging tools and introspection tools, and I was like, huh, interesting. Like, it's in this world, it's kind of hard for us to imagine that, I think. So that is my rant, basically. I kind of tricked everyone, or I tried to trick everyone in this room in my abstract and throughout this talk, because this was actually a talk to everyone in this room that is like a cry for help, which is, I really want to bring the values of the C++ community to robotics. Zero-cost abstractions is a phrase that we need because we are doing real-time problems that are safety critical, and we need people to write performance-safe code. And we also, these are complex problems that we need generic libraries for that can be reused and passed around to people. Otherwise, we're just never going to get there. So if you find any of this interesting, then please talk to me later or email me. I forgot to put my email on the slides, but I have business cards. Thank you very much.
Any questions? We have 5 minutes for questions.
5 minutes. 5 minutes for questions.
Any questions for Jackie?
You talk a lot about performance and getting things done quickly, and then you mention floats all over the place. What about fixed point implementations, integer math, and stuff like that?
I actually have a microphone, so yeah. It's not something that I've benchmarked a lot. The thing about fixed point is, well, yeah, existing libraries don't have interfaces for that, but I can see how you could probably hack Eigen. So Eigen is a very popular and awesome, in my opinion, expression template library for matrix multiplication, and you could probably hack Eigen to have fixed point, and it would be interesting to benchmark against floating point. Yeah, I just haven't done it.
Someone else?
So you say robotics need high-quality, well-documented real-time C++ libraries right now. Can you maybe mention like 1 or 2 specific things that are like the top of your wish list? Like this specific real-time problem, we don't have a good C++ library for that.
Oh boy, okay. That was kind of trying to be the point of the talk, but so let's see. There's octree data structures is one like very specific thing, and then some tooling for visualizing and building those. So there's another of like common popularly used open source frameworks is this thing called Octomap, which has it was designed for take point clouds, accumulate those into a grid of the world based on like you've mapped out the entire world around you, and then put that in an octree, which is very efficient to access and has this spatial representation. And it's like needs a facelift. Gosh, yeah, I could talk for days probably. Yeah.
Any more?
I just wanted to comment that I saw dlib for the first time, but looking at its template interface, I think it would be quite possible to add like a HANA-style layer of sexiness around that.
Right. Yeah. Rather than like. Yeah. I don't actually. I would have to think a bit more about if the compiler would be able to optimize the like graph representation of a network better than like if you deserialized a representation from like JSON or whatever. That would be super cool. And also if there could be a better interface for specifying or even like designing it at compile time. Yeah.
Okay, it's finished now. Thanks for Jackie for an awesome presentation.